You're like, All right, so this is arguably one of the most exciting units that we will have to cover today, the radiation units and measures, which is why I've got the intelligent interruptions going on, is for whatever reason, when we talk about the superpowered awesomeness of radiation, the more I talk about how superpowered and awesome it is, the less and less power you as students have. And I've been there too. There's free coffee over in the library. Okay? All right, here's some objectives. We need to be able to convert between conventional and SI units, just as an exercise, and to become really, really fluent with scientific conversions, we'll need to be able to calculate a dose area product. That's what DAP means. We're going to list occupational dose limits. And in case you missed me say it the first time, we're going to list occupational dose limits. All occupational dose limits will be listed. And there will be an exam question on every single one of them, because they are important. And we're going to illustrate various detection instruments. So let's start out with these conventional units. Exposure. One of the easiest ways we can think about exposure is it is the intensity of radiation. Exposure is generally measured as an electrical charge in air. So our textbook talks about how it talks about the intensity of a radiation incident on a surface, but generally it is measured as the radiation within a volume of air. That's how the SI units measure it. These ionizations produce electrical charge, and then we can measure that electrical charge, and the unit of measure traditionally, conventionally, was the Rankine, named after the discoverer of X-rays. That is different from dose. So exposure is just ionizations in air. Dose is what happens when those ionizations hit biological tissue. Okay? So we are not going to use those terms interchangeably. They are very scientifically specific terms. And so the unit of, conventionally the unit for this biological impact of exposure is the rad. And 1 rad, like the textbook says, equals 100 ergs of energy, or energy per gram of tissue. Okay? Don't get lost in the weeds on that. It just basically means it produces X amount of energy in a tissue. So this applies directly to radiation weighting factors, because different types of radiation have different amounts of energy that they deposit. Okay? So for example, photons, and that could be either X-rays or gamma rays. When I say photons, I could be talking about X-rays or gamma rays. They have a weighting factor of 1. X-rays and gamma rays, just a weighting factor of 1, because they have a low linear energy transfer. They do not transfer much of their energy to tissue. Alpha particles have a weighting factor of 20. That means that of the same dose of alpha radiation and X-rays, the alpha radiation is going to affect you 20 times more. It has 20 times the biological impact. So that's why we need to have these radiation weighting factors. All right, that was time 1. All right, you've got a minute. Okay. So if we want to know how biologically effective a radiation dose is, we need to consider not just the weighting factor for the radiation itself, but we need to put a weighting factor for tissue. And I apologize, but when the slide was imported, it didn't do this as a sub R or sub T. So make sure that in your notes, it's normally W sub R and W sub T. It should, on the PowerPoints, it should have that, but just this importation process lost it. So for conventional units, that is the radiation equivalent in man, rem, kind of a sexist title, but that's what it was conventionally. And we see a lot of that kind of conventional wisdom in a lot of things. Like, for example, radioactive materials used to be referred to as daughter products, right? So there's a lot of weird kind of conventions like that, which is one of the reasons we're getting away from conventional units. But in general, for X-ray, 1 Rankine of exposure equals 1 rad equals 1 rem. In general. And that's from page 711 in our textbook. And the reason for that is we have 1 Rankine of exposure in air of photons. The weighting factor for photons was what? 1. So exposure times 1 equals the same thing, 1 rad, right? And the rem, when we consider whole body exposure, everything kind of washes out. If we want to know what someone's dose is to an organ, that's where stuff gets really complicated. Okay? But if we're talking about a whole body, how this has affected their whole body, then we're good with just that. Finally, conventionally, the unit for radioactivity is named after Marie and Pierre Curie, and it is 37 billion decays per second. That's a big number, right? But it is telling you the rate of decay. Now, conventional units are garbage, and so I'm sorry that you read so much about conventional units. It's one of the few bad parts about this textbook, and there are some errors in here that I'll point out as we move forward. Trying to make sure I found it here. Yeah, we'll look at an error in the textbook as well. This is not one of the stronger parts of this text. SI units, everything is reported in SI units now, at least for the registry. But it's kind of like feet versus kilometers, right? The rest of the world may be chugging along at 30 kilometers per hour. For us, it's going to be 45 miles per hour. Gosh darn it, Same with conventional units. The NCRP and these government licensing bodies continue to use conventional units here in the United States, even though the rest of the world has moved over to the SI system. The ART has now moved over to the SI system as well. Okay? There's a lot of good reasons for that. The unit for exposure in the SI system is the coulomb per kilogram. And so that again is a unit of charge within a kilogram of air. It is very specifically defined as the amount of charge that these ionizations produce in a volume of air, in a very specific volume of air. Dose then will be joules per kilogram, and which is the amount of work done per kilogram of tissue now. But we can express, we do have a little bit of flexibility here. And so with the gray, we may see gray sub lowercase a, which is gray in air. And so that is essentially still a unit of exposure. Because again, exposure is defined as ionizations in air versus gray sub T, which is gray in tissue. And so now it has just turned into a unit of dose. Within the SI system, equivalent and effective doses are both expressed in sievert, and these will look fairly similar to the conventional stuff that we were just talking about. So a radiation equivalent is the dose expressed in gray times the radiation weighting factor, right? So it is very similar to the rad. But in this case, that's going to equal an equivalent dose, because it is setting the dose equivalent across different radiation types. So with this system, it gives me much more scientific accuracy, because I can look at someone who is perhaps exposed to a particle and a gamma ray and a neutron, and I could weight all of those different exposures across those different types of radiation, and it will be expressed in sieverts. That's the equivalent one. The effective one is going to say dose times the weighting factor for the radiation times the weighting factor for the tissue. And that's going to give us an effective dose. That again is also expressed in sieverts. Okay? So if you're talking to a health physicist at any point, I'll stop there. All right. You've got a minute. So for the SI unit of measure, radioactivity is the becquerel. I am not as interested in that because we are not sitting around playing with radiopharmaceuticals. Does that make sense? Okay, so to convert, the way the textbook has it mapped out is like this. 1 gray equals 100 rads. Gray is the larger unit. The way that I remember it is 1 rad equals 1 centigray, because the rad is the smaller unit. That's the way that I tend to remember this. As I like a 1-to-1 comparison, 1 rad equals 1 centigray. So we could express both of these in scientific terms like that, using centa and milli and things like that. That's the unit of conversion. Fortunately for you, when you get to the ART registry, it will tell you the patient received X amount of gray, parentheses, X amount of rad, right? They will do the conversion for you. Yay. I do not. I expect you to know how to do this. Yes, I know. The reason why is that's more true to what you actually will be asked to do in clinic. There will be situations where you need to know how to convert. Okay, dose area product may also be referred to as the DAP. Okay. Basically, this is the radiation biology way of thinking about collimation. That as we open up the collimators and we're exposing larger areas of tissue, guess what? It causes more biological damage. Right? So we keep our collimators closed. Why? To minimize scatter and improve image contrast, but also to reduce patient dose. So the way that we calculate a DAP is we just take the dose and we multiply it over the area that was exposed. This is talked about in our textbook on page 711 to 712. So, let me see if I ask us to do that right now. I am not necessarily interested in you being able to calculate a DAP at this point in time. But I do want you to understand that as you increase the area of interest with your collimator, as you open up the collimator more and more, you are increasing patient dose. Okay? And then we have a way of quantifying that as a DAP. It will probably wind up moving forward being a primary way that we calculate patient dose in X-ray. Okay, let me move this slide up just a little bit. This is from NCRP report number 116, which is in your key terms. You can pretty much just paste this into that area or copy it into that area. There's really no other way to express these numbers than the way they are expressed. Every single one of these we need to memorize. I don't think I'm missing anything. Does anyone who's looking at the PowerPoints, is there anything missing?
You don't have the embryo fetus one. You want us to know that?
What is it? Is it the per month thing? Does it not have the month?
It's on the quiz.
Okay. Yeah, we do need to know both the monthly and the total for that.
So the public exposure annual is not on there.
Okay. Well, I will refer you back to the key terms then for that information. If there's any part of this slide that's incomplete, please refer back to the key terms. It has it complete there. Let's talk a little bit about these numbers. So the whole body effective dose limit for anyone who's occupationally exposed to radiation is 50 millisieverts according to the NCRP. Okay, this was a report that came out in the mid-90s. So that's a whole body effective dose. That is what you receive on your radiation badge.
For a lifetime?
For a single year.
For a single
That's an annual dose.
Okay.
We can calculate also what a cumulative lifetime effective dose would be. It is just your age in years times 10. That will give you the amount in millisieverts. But we don't need to worry about that right now. What we need to understand is that for us, as occupationally exposed individuals, our annual dose limit is 50 times what the U.S. public's dose is. You notice here the effective dose limit for the U.S. public is 1 millisievert. Another thing that stands out here, and I think this is interesting, is we have infrequent exposure 5 millisieverts. That is diagnostic x-ray. Anytime we take a patient back and we do a chest x-ray on them, that is the max that they are permitted over the course of a year. Yes?
Can you repeat that again?
I sure will. As an x-ray tech, you are going to be receiving potentially 50 times what the U.S. public receives in your radiation exposure. Okay? And also related to that, that is a whole body dose. Here, the effective dose limit for the general public in the course of a year is 1 millisievert. Now, I want to say a couple of things about this. First of all, we are the only industry that is allowed to intentionally expose the U.S. public to radiation. According to U.S. law, right now, we're the only occupation that's allowed to intentionally expose John Q. public to radiation. That's not always been the case. Right? I don't know. I know I surveyed the class to see who here likes Stranger Things, right? It's an interesting show. Part of what that show is built on is some of Tennessee's history, right? That there was a remote government site here near Oak Ridge where the Department of Energy was doing some nefarious stuff, right? And when I say nefarious, does anyone know what that word means? It's a fancy word for kind of evil stuff. Like they were injecting people with pharmaceuticals without their knowledge. They were feeding radioactive materials to kids. They were doing experiments. There was a housing project called, I think, Let's or something like that in St. Louis. They were spraying radiopharmaceuticals off the roof of the housing projects to see what would happen to people who were routinely exposed to radioisotopes, right? Now, that's not all they did. They did do some good and helpful work, and a lot of what we know about nuclear medicine came out of that area of the country. In fact, PET-CT was invented in this state because of the work that was being done there. So there was some good stuff that came out of it as well. But we are now the only people, not Department of Energy, X-ray techs are the only people allowed to expose the public intentionally to X-rays. Why would that be the case?
Diagnostic purposes.
Yeah, there is a benefit. There's an expressed benefit that the patient enters into a contract with us. And that implied contract is, you are going to render me a service, so I will trust you with operating this equipment safely. Right? Now here's another weirder question. How come then, if that's the case, is it okay for us to get 50 times the dose that they get? What's the deal with that? Any thoughts on that one? That's a weirder question.
Say it again.
Why is our dose limit? I'm not saying everyone needs to run out and get 50 millisieverts. And in fact, as students, y'all are more this. As students, in the course of your students, one of the reasons we're such hawks about you holding patients is, according to law, y'all are still here. All of your technologists are here. So for them to say, hey, will you help me hold this patient? No, I won't, because that's against federal law. This is my dose limit, that's your dose limit. Right? As a student, you are still here. But why is it okay once you are licensed as an X-ray tech, after you've got that RTR behind your name, why is it okay all of a sudden that your dose limit jumped up here? That's part of it. I'll answer this question and then we'll
We
do.
just have to do more exams a day.
We do exams. It actually is a weirder thing, right? You have to think about population groups. So which has the larger population? The population of the United States of America or the population of X-ray techs who work in the United States of America? The population of America, right? So when we think scientifically about this, and this is a little creepy, but this is actually the reason why. The odds of an X-ray tech marrying another X-ray tech are less than the odds of an X-ray tech marrying someone who's not an X-ray tech. Now, why would that be important? Well, the odds of them then having a baby, right, that could have received a significant dose from both partners is that much even smaller, right? So that's the kind of weird math that they have to do to come up with this stuff. They're thinking about a genetically significant dose. When we irradiate a population of people with a whole lot of radiation, what is the amount that can produce genetically significant mutations in the next generation? Right? So as X-ray techs, we're basically carrying a burden for the rest of society. That burden is then diluted by society in turn. Right? And this is something we've been tracking for a long time. So we can look statistically at that. If you get really interested in this stuff, I actually have an article from June in the ASRT journal that talks about how we came up with some of these numbers. So for the time being, I just want us to understand, memorize that. It's not changing anytime soon. Okay. Let's take a minute and come up with a response to what we've talked about so far, and then we'll take a little break.
James said I ain't get asked again.
Okay. All right. Who do I have here? Miss Parker, it's you again. Sorry.
Does she like have to go like, I have a question. I actually have two questions.
I got 3 questions.
You want to take? You want
I
to
mean,
give
she
up your
already
turn?
got
What's that supposed to mean?
it. Go for it.
Yes, go for it.
Okay. My first question is back on the other slide about the conversion. Can you like show us an example of how to convert it from to the the red to the C gray or whatever?
Yeah,
Since we have to know it for.
that's our activity. We'll be doing it. I promise you, I'll show you how. Yeah, you're gonna get to do it, and we're all gonna get to do it.
Okay.
But
That
just
was my question.
to answer, just to show you real quickly. Say we had 20 rad, right? And I want to know what that is in gray. Basically, I could just say it also equals 20 centigrade, right? And then if I wanted to then convert it to gray, I just need to move my decimal points around. So I could just hop these over 2, 1, 2. It equals 0.2 gray. That's the way that I tend to do it.
Okay.
Is there a number you multiply that by?
Well, it's just 1 rad equals 1 centigrade. If I wanted to figure out what it is in gray, I could also just multiply it by 0.00 or 0.01, I think.
Yeah.
Does that make sense? So if I want to know what it is in centigrade, I just multiply it by 1. If I want to know what it is in gray, I multiply it by 0.01. Another question.
My other question is like unrelated to what we're doing, but when you were discussing public exposure and you were talking about the things that they were doing, like I guess the X-rays off the whatever, or were you talking about like chemtrails, like when they discussed?
I'll show you what I was talking about real quick. It's not chemtrails. It's different. I don't know a lot about chemtrails, and I don't know a lot about this, but if you go to Wikipedia, what's this? St. Louis Housing Project. Yeah, Pruitt-Igoe. It's actually designed by the same architect who designed the original World Trade Center towers, Minoru Yamazaki. But if you look down here at design and construction, it has secret Army testing. In the Cold War, the Army sprayed zinc cadmium sulfide, a radioactive chemical, from motorized blowers on the roof around the Pruitt-Igoe housing projects. Now, this is true. This is not like fake news or anything. And if you get interested in the secret side of radiation biology, the Clinton administration released a really thick book. I have it up in my office called The Human Radiation Experiments, and it documents all of the government-funded research that was done from the end of World War II to 1973 or 1974, largely in secret, without people knowing. This was one of the last, this would have been fairly late in the game that they did that. So yeah, weird stuff. But it is, I'll tell you this, one of the reasons I mention it is just to underscore how much people are trusting you when you say things like, I'm going to shield you for your protection. I know that's just a generic thing that we say day in, day out, but they really are trusting that you understand this and that you are administering the radiation safely, because there is this. There is the Stranger Things side to this stuff that we have to be honest about. And there is uncertainty here. And there's even things like coercion and things like that here. Does that make sense? So it is. I think it's different from the theories I've heard about chemtrails and stuff. Good question, though. All right, the other person that I've got, let me see, is Mayfield. There you are right there. See, random.org. Oh, it switched it over. Sorry. Stand and deliver.
What if two X-rays, two X-ray techs did get married and have a baby? Like, is that a bad thing, or
That's a great
where
question.
were you going when you said that?
Okay, good question. Good question. No.
Right away?
Two X-ray techs can get married and have a baby. That has happened before, right?
I'm concerned about this too.
Yeah, right.
When you said that, I'm like, huh.
What they're looking at is a genetically significant dose over a very, very large population from generation to generation to generation. So the research around it was done initially on fruit flies because we can expose a whole lot of fruit flies to radiation and they reproduce pretty rapidly and their chromosome sequence is very similar to ours, right? And so we were able to examine fruit fly populations and come up with some of this information, right? But what I want to stress to you is that this number right here, even though it is 50 times what the U.S. public receives, is still well below the number known to cause genetic mutation from atomic bomb survivor data. That number is 0.4 sieverts, right? So if we were to do the math here, let me see, 0.4 sieverts, we want to figure out what that is in millisieverts. We need to multiply it times 100, I think. So
Brandon, when that time comes, you just need to worry about it looking like CD instead of
that would be 40 millisieverts received as an acute dose.
There won't be no birth effect, will it? Or cause it?
One thing that I will say about this, okay? I did work at a facility, and there was a number of X-ray techs that were married to other X-ray techs, and they had a lot of female babies.
I don't want a female baby. I want
Nothing you anyway.
We don't need another one of you.
But the concerns that we have are more for things that occur within the natural population already. And again, this would have to be an acute dose of this is an annual exposure limit. You would have to have an acute dose close to your yearly limit in a single instance for you to significantly increase the risk for harm to a fetus, if you get what I'm saying. Now, if I was an X-ray tech and I was married to another X-ray tech and I wanted to know that how to reduce the risk of this stuff being passed on to the next generation, the two things that I would do is I would wear a radiation badge and I would wear a shield. And I would be perfectly fine. These dose limits are produced to make sure that the risk factor for our job is closer to that of the risk factor for an accountant or a lawyer, right? The risk factor for our job is not the risk factor for underwater welder or ballistics expert in the military, right? But it is up to us to practice our job safely. Does that kind of answer your question? So you're perfectly fine to go out and have kids. It's not going to mess up anything there.
I don't want girls though, so I may have to change if I get boys.
I don't know about that. I'm going to let you dig yourself in on that one. All right. We've got one other. Oh wait, we did both of them already. All right. Let's take a 10-minute break, and we'll come back. 10 minutes. Get up, walk around, get some coffee.
No, I was probably trying to whoop saw and I showed wrong.
Thank you.
No, I was probably going, don't kill him. Don't kill him. Yeah.
Yeah. Keep it quick.
Yeah. Yeah.
I didn't know if you had somewhere else to go.
No, we're good. Yeah, you bet.
What?
I'm not saying now. You, for some reason,
I just keep paying attention on your phone.
Okay.
No, it's different.
That one probably want for you.
No, it's
She want you to be right here like that.
I Okay, do I need to get my phone? You say you doing it so you can see your face.
So tell him when you start snapping pictures, it's for a reason.
I'm gonna put the camera right up there so you can see.
I don't know facial expression. I'm like, what face? I'm just sitting here.
Fix your face.
Sound like somebody's mom. She didn't say that when she was talking about that girl. What is she? It's just a little face. It frowns up too. It's like, oh. She felt that was deep down. I'm just saying. That outfit just ruined her day.
I thought in physics I had it.
Well, wrong with that.
Right.
Still gonna review the old stuff. Me too. But, I mean, I just know it's leaning more towards Peter. I'm probably supposed to be down this game at 3. Did I hear that wrong? December 5th. So it's the program.
Is the age of credit? Is the age of credit?
Program?
I don't remember when that happened.
That's turn it down.
I say this because.
I mean, he said it's gonna be doing.
What
It's
is
the
your
5th one. It's the 5th one. Susan? I'll be there. I'll be there. I don't know where to get the work from. You're the first person that said that, that's why I'm messing with you. Like I
Well,
said,
thank you.
it's just how I look, I look angry,
No, you don't look angry. She looks
frustrated, or
You just in this class, yeah, in this class you just started. For some reason started this cold. That thing over there.
Look it up right there, one line. Oh, we're talking about you. So that, when you can't control those things, your whole day, what's she saying? Yeah, yes, you did. What you
Okay.
say? What say it to you? What you tell her, what you said? Like, one outfit. Your face. Ooh, I can't even do it. Your face was so serious. It was so been out of shape, boy. Right. Yes, ma'am. You. Now. Next time she walks in the outfit, I'm never on you.
What time? I need to be off. I need to take off.
You back that stress? Have you done? You back that stress? That's why you look like this.
I'm ready to go.
Yeah,
Has
it's
it already?
due Thursday.
It's taking too long.
What's the third question?
Is that hard?
What's good for hard? Oh.
We ain't had no
I
problem.
thought I heard you
Just
say
since you
13
came in,
questions.
kick that
I was like, I
door.
don't know anything 13.
Push the box over. James throw shade
Yeah,
on
I am kind of bummed out.
That girl might want his friend.
No, that I may have a higher chance of having girls when we get older.
Girls are fine.
No, they're not.
Yes, they are. I agree, boys are better.
And there's a higher chance of them playing soccer, and I hate
So,
soccer.
Mr. Roberts, what have you done with your spinner
Just sitting like
since they
soccer.
are, did you see where they were, they pulled some from the store?
She's gonna-
Really? Why?
There's something.
Have a lot of lead.
Oh, I believe that. Yeah, they got bearings in them. Yeah. I mean, I'm not terribly worried about it.
Just taking an X-ray and.
Oh, that's just that loot crate box.
Sensor
Yeah,
in
no,
the
please.
gown.
No, I was
Have you seen that?
getting it back from the thing. Miss Parker, don't be so suspicious. Fix your face.
Thank you. Shade.
That's right.
Shade.
Because I looked at my.
Yeah, she gave me that. Yeah, she gave me that face. Yeah.
We taught him something new, yeah.
Mm-hmm. I learned something. I'm still learning. Y'all, I learn something new from students all the time. I appreciate what I learn.
So
Not
go ahead
keeping
and
it
fix
down.
your face.
Hmm.
Didn't get from us.
I took an X-ray the other day,
Mhm.
and there was a sensor in the picture. And I asked the tech, I said, "What is that?" She goes, "I don't know what that is." So we went over there to go check it out, and there's a sensor in those gowns.
Really?
Mm-hmm.
Yeah, so they don't get stolen, they'll charge you for them.
What?
And it showed up on your
It showed
X-ray.
up on the X-ray.
What's the sensor for?
I don't know.
This Kathy and Memphis was telling me, like, don't stockpile the linens, because all of them have sensors. And like, does it make it back through the laundry room or whatever? They charge the department for it.
What on earth?
I didn't know they showed on x-rays, because I can't even.
I know they charge
What?
for it.
All of the sensors on
It kind of looks like a metal plate.
Huh.
That's like Sarah had a patient, and she just had a t-shirt on. She didn't want a gown. No matter, she was fine with wearing a t-shirt, no bra, whatever. And it was just a white shirt, so you can tell like there was nothing on it. And Sarah took the X-ray, and we pulled it up, and there's like on her chest a right marker, but it's not.
Like a disposable one.
We couldn't find. It was like not on her body. It wasn't in the PA, but it was on the lateral. We're like, we don't know where it was.
We
But
couldn't find it either.
when she went,
Maybe in the
when she
Bucky or
turned
something?
around, we looked in the Bucky. We looked everywhere on the everywhere. We even looked on her shirt. We're like, we looked on the ground to see if it fell off, like one of those sticky lines.
Yeah.
We're like, it was weird. We were like losing our mind.
That is wild.
We didn't know where it came from.
I'm sure she's probably a little weirded out by that too, like trying to figure out what are they looking for on these. Yeah. All right. Let's get, the rest of this is going to move pretty quickly. Okay.
Is that your alarm you wake up to in the morning?
Mm-hmm.
I would never wake me up, ever.
I don't like.
Put me in a deeper sleep.
No, I need something quiet. Most of my electronics I keep pretty silent.
No, mine has to be loud and annoying.
Okay. So, one thing I want to point out more to Brandon's question, if you look on page 716 in the textbook, it talks about a genetically significant dose, and if you see there, it does make a case for a genetically significant dose of 20 millirems per year. It talks about how that works. And before I forget, on page 722, there's something that's incorrect in our textbook. Figure 41.7, that is not a thermoluminescent dosimeter. That is an optically stimulated dosimeter. So it's an OSL. It is what we all carry. We carry OSLs, optically stimulated luminescent dosimeters. So we're going to talk more about that here in just a minute. But while I was thinking about it, I wanted to go ahead and correct that error. That is not a TLD.
What does the L stand for?
We're going to look at that right now. So for monitoring personnel exposure, we do this to ensure that occupational radiation exposure levels are kept well below those effective limits. So the game is not to try to hit your effective limit, it's to keep it well below that. And honestly, I've worked in X-ray for close to 17 years. I have not known any technologists that have exceeded their annual dose limit. And I've known a lot of technologists who have done a lot of really stupid stuff. All the fail-safes, all the safety measures that are there in place in the department work. But the way that we're going to monitor that most closely is with this guy here. And this is an OSL. And let me see if he's got a spelling of it anywhere in the textbook. I don't guess he does. But it's optically stimulated luminescent dosimeter. Okay. Now, one thing that I'll stress in radiation biology is this thing is very effective for capturing exposure to X-rays and gamma rays. Everything to doses that are well below the diagnostic energy range to doses in the therapy range, up to 40 mega electron volts, which is very, very big. It is not very good at capturing exposure to particulate radiation. So turn your badge over if you want, and let's see if anyone has a little yellow packet here on the back part of your badge. Does anyone have a little yellow packet here? The answer is no. This little yellow packet, if you see, it says neutron compound. It's an optional additive that you can add to this OSL if you want to capture what your exposure to neutron contamination would be. Otherwise, this thing does not detect neutron contamination. You might be thinking, where could I possibly receive neutron contamination? And the answer is in the radiation therapy vault. After they energize that linear accelerator, that high-powered X-ray machine, it actually does produce things like photodisintegration events where photons actually destroy a portion of the atom and neutron contamination results. So the therapy vault is no joke. Go in there only with a therapist, okay, and follow all the rules. But these badges are very, very helpful. The main thing that we use them for are for personnel monitoring, and we use a monthly or bi-monthly report to track people's exposure. This monitor does not indicate to me immediately whether or not I've been exposed to radiation, like whether I'm being exposed right now. I have to wait a month or two, and then I get my report back, right? So in addition to having monitoring like this, we also need monitoring like Geiger counters and things like that. Wearing an OSL is required anytime a person working has a chance of receiving 10% or more of the annual occupational exposure limit, right? 10% or more. So that would be 5 millisieverts or greater. Those people need to be monitored in any given year. Most facilities issue these dosimetry devices when a person could potentially receive 1% or more. This is going to help us track people's working habits, and it is going to help us determine what the occupational exposure was to the whole body. This is designed to track dose to the whole body. Within this device, though, there are filters of different types of metal, and that's what we use to determine what the dose to someone's eye is, or the dose to the skin. Okay, so we look at different filters, and we make a determination of, okay, given the energy range that got through that filter, that we'll call that an exposure to the eye, or the energy range that got through that filter, we'll call that an exposure to deep tissue or the body.
So that thing measures different parts of your body? Is that what you're saying?
Not necessarily. It only measures in this area, but anytime your body is exposed to radiation, any kind of flux, there's different filters inside of it which determine how deep the radiation was able to get. So the lower energy radiation, they're going to say that was an eye dose and only got to the lens of the eye. The higher energy exposures that we received is going to say it's a body dose because it got to deep tissue. Does that make sense? It's a good question.
So-
Yes.
So you're saying like in a report, like it'll separate
Yep.
the eye and, okay.
If you look at your dose report, it will have it separated out.
That's what I was asking.
Mhm.
Yeah.
It will have it separated out on a dose report. These should always be worn at the collar level. I'm not even wearing mine quite appropriately down here. It should be more up here at the collar level. At the front of the body, anytime I'm wearing a lead apron, I will wear it outside of the lead apron. If I became pregnant and I declared my pregnancy, it can happen, y'all. I read about it in the newspaper or something. I don't know if that was real. But I would have to declare that I am pregnant, and then from that point on, I would be issued a second badge that I would wear at the level of baby, right? Anytime I'm wearing a lead apron, it would be underneath the lead apron. What was that?
You don't have to declare we're pregnant.
Correct. You do not have to declare that you're pregnant.
Why?
You don't have to. All right. Okay, I'm going to speed on along to the end here. No more intelligent interruptions. We'll knock this out. So the main form of personnel monitoring that we're going to use is an OSL. Okay, the optically stimulated luminescence dosimeters. These OSLs that we scan with a laser, they produce light, and that's how we measure the amount of radiation that the person was exposed to. And from that, we can calculate a dose. Right? We know what the exposure was in air outside the patient's body, and then we can just multiply that by a weighting factor here for the radiation type, which is 1 for X-ray, and we know this is what your dose is. We can express that in sievert or in rem. Are you tracking with me? Okay. Some texts will still call this a film badge. Film badges literally had film in them. This does not have film in it. But that's just the term that we got accustomed to, and so they use those terms interchangeably. But the way the film badge worked was it had a portion of X-ray film inside of it, also with filters. The person would wear that for a month or so. We would develop the film, and then we would measure the density on the film, and we could extrapolate from that density to a certain amount of radiation exposure, and we could say then, this is your dose, right? We might also use TLDs, which are thermoluminescent dosimeters. Those are used primarily in the form of ring badges that the nuclear medicine technologists wear. Their ring badges are TLDs. They're very similar to these in that they're exposed to radiation. A crystal traps that exposure, and then the material is heated. So TLD stands for thermoluminescent dosimeter. It's heated and it produces a glow curve, right? And that glow curve, then again, we relate back to a certain amount of radiation exposure. That's in your textbook on page 721 and 722. The final one that we talked about, the sexiest one, is the pocket ionization chamber. That's the one that will win you all the awards at your science fair. But and it gives you an instantaneous reading. It operates very similar to a Geiger counter. Okay, and it allows for instantaneous reading. Generally, it's not worn for longer than a day before it needs to be reset. So a reading will be made, and the device will be reset, and then it'll be ready to go on and be used again. So here is the OSL broken down in a little bit more detail. They're great for beta, X-ray, and gamma radiation exposure. They have a copper and tin filter inside of them, as well as a little window, which you can see on the front of your thing, and that goes directly to the aluminum oxide detector film. I think I may have said cesium iodide before, and I apologize for that. It is accurate as low as 0.00001 millisieverts or 10 microsieverts, and the sensitivity ranges from 5 keV to 40 MeV. So that's well below the diagnostic range into the therapeutic range. You don't necessarily need to memorize these numbers, just know that it covers a broad spectrum of energies. And then it is crap for any kind of particulate radiation exposure. It does not capture those. So you don't need to be wearing this into the PET CT bathroom and thinking that you're getting a good reading there. In fact, you don't need to be using the PET CT bathroom at all. Let's talk about radiation survey. The two types of instruments that we generally use in the hospital are Geiger counters and sodium iodide scintillators. And they can be used in two different ways. One is as a rate meter, and the other is as a scalar counter. A rate meter gives you an amount of radiation exposure over time. So in this case, it can be read out in millirankins per hour. It's one of the more common ways that these things are calibrated. And they provide an analog display. So they have that classic sound of or whatever, like that, like a robotic dolphin.
One more time.
This here is a Pancake Geiger counter, and one of the reasons that they have us learn about it, one of the things I want to point out to you about this, it's on your textbook in page 723, right? Figure 4110. Look at that figure very closely and tell me why we might be learning about this as X-ray techs. It has an anode in it. Thank you. It is basically the opposite of an X-ray tube. An X-ray tube is built to produce X-rays, so it has an anode and cathode. This is produced to detect X-rays, so guess what? It has an anode in it. So it is the absolute inverse of an X-ray tube. It does the exact opposite thing, but it is still sucking electrons towards an anode in order to detect ionization within a chamber of air. So that's why they have us learn about it. Scalar integrate counts over a selected count time, and generally if an instrument's fancy enough to have the scalar capability, it will also have a rate meter mode. A lot of times their displays are digital. This is what we use if we need an instantaneous reading of, for example, this is what your X-ray exposure was. Not this one and this one and this one, just this one. This one's going to tell you everything. Background radiation and everything. It's just constantly going off. This one you can tell it, I just want you to sample one. So here's a little bit more discussion of the Pancake Gm Detector made by Ludlum in Texas. It's kind of the workhorse of the industry. Almost every facility I've worked at has had a Ludlum GM counter sitting around. So it has a tungsten anode with a glass bead on it and a steel cathode around it. That is the tube, right? There is a mica window here, which all that is just thinner than aluminum. It's like aluminum but thinner. So it allows the ionizing radiation to get into this little chamber here where there's some kind of gas. It ionizes the gas, and the electrons from the ionized gas are propelled towards the anode, and the anode says, okay, an ionization occurred. It makes its little weird dolphin sound. Okay? So that's really all you need to know about Geiger counters, is that they function exactly like an X-ray tube. Sodium iodide scintillators are the other ones that we use in the hospital, and these are typically used as well counters. They are a scalar way of measuring specifically an amount of radiation exposed. Their background readers are going to be higher, so a lot of times they're encased in lead. So if you ever go into the nuke med department, try to pick up the well counter, you're going to be surprised by how heavy that little tiny thing is. All you need to know about this is that it is not operating like a Geiger counter. It is using scintillation. So sodium iodide crystals are forming light, and that's what's being read. So if you notice, it has sodium iodide, a photomultiplier, and then a way of reading that out. And you're going to see all that stuff again when we talk about digital X-ray. All right, thank y'all.